No, I just should work. Okay. Okay, so I want to start with a question. So what is the jet? Because the process I'm starting is really a quark jet going through a medium. So in heavy ion collisions, a jet is a collimated beam of particles produced by the splitting of a common ancestor, like a quark or gluon. So if it's from a common quark, and then it's a quark jet, or from gluon, then it's a jet quark. So on a very sketchy picture is that in the high energy collision, and then like that's the initial quark, and then the split into multiple gluon quarks, and then in the end it goes through the hadronization, and what is being measured in the end are the jet from experiment. And then so this process of the splitting, it does not happen just in vacuum, but during heavy ion collisions, like a dense medium is produced. So the jet goes through the medium. It can also be think of as a probe or matter, and which can be used as a tool to understand interactions. And so the studies on the jet focus on different regions, and for many people doing the theoretical study, including myself. So I'm focusing on this initial region where the quark, it starts from a high energy moving quark, and it can emit a gluon, and it also interact with the medium through like which is illustrated as this vertical red gluon line here. So for me, a jet is an energetic QCD state that evolves and interacts with the medium. And so this is a fundamental process that can happen in many different kind of scenarios. So for example, in the deep inelastic scattering, when the electrons scatter on the proton heavy ion, so it goes through a virtual photon which can further fluctuate into quark antiquark pair, and then the quark antiquark pair, it further interacts with the medium or the background field generated from the proton on heavy ion. So here the quark with the medium is like a small piece of the fundamental process. And also similarly in the proton nuclear scattering, when I think of proton and heavy ion collision, the quark comes from the proton, also goes through the background field generated through this collision. And of course, also in the heavy ion collisions, a jet is also produced, and it traverses through the medium produced in the collision. And so in all those kind of different scenarios, as I mentioned, the quark jet scattering of a color field is a fundamental process. So on the space-time diagram, we think of, so this on the TZ diagram, so the quark is moving fast along the positive z direction, so it's denoted, the word line is denoted as this. And whereas the heavy ion, which is described by the background field, which is denoted as this red band here, is going through like the negative direction versus the quark. And then at high energy, this target has many gluons. It can be described as a classical gluon field, known as the color glass condensate effective theory. And so later I will give more detail on this. So I used the MV model to describe the background field. And whereas for the quark, it is treated as a quantum state of QCD. So as a very sketch diagram of this process is that when the quark goes through the medium, so while it's interact with the medium background field, it can also emit and absorb gluons. So what has been already established, and also what is the approximation in the existing study, is that one is the Eichner limit. So what it means is that since the quark is a high energetic jet that traversing the field. So the Eichner limit meaning that the quark is infinitely energetic. So here the P plus is defined as P0 plus Pz. So you can think of the quark moving at the speed of light along the z direction to take this to infinity. And by making this Eichner approximation, the calculation is highly simplified. So you can think of this way, since the quark is moving so fast, so it does not have time to change its direction in the transverse location, so which is the R perp. So in this limit, the R perp will not change. And what can change is that its transverse momentum, the P perp, it can change because it exchanges the transverse momentum with the background field. And also the color quantum number could also change through interaction with the background field. And then the spin or the elastic state of the quark remains the same in this limit. So that's the Phys picture of the Eichner limit. And in this limit, the evolution operator can reduce to the Wilson line. So it's essentially an Eichner scattering amplitude. So it resums the A mu, so all those macro scattering with the background field in the past order exponential. And then going a little beyond this Eichner limit, what these people do is to study the sub-Eichner effect. For example, here one could do like through all those Eichner scattering, one can consider like one scattering like is a little bit harder so that it can change the transverse position of the quark only through here, and while all the other scattering remains as Eichner. And then what has also been studied like in this kind of studies is to use the perturbative approach. So such that it's the calculation is expanding power cell coupling. And in negative order, there's one gluon emission. So you could still have multiple scattering with the background field, but only one dynamical gluon is emitted. And then NLO could have two gluon emissions like this. And then the calculation is usually on the probability level. So like one calculates the cross section by doing the M and the M dagger. So the differences here is that, so in our approach is that we use a non-perturbative approach. And so this will allow us to easily go beyond the Eichner limit. And also we will do the calculation on the amplitude level. So such that we track the jet and the evolving quantum state. And so we do numerical simulation and the real-time simulation. So these letters can access to also the intermediate state of the evolution. So in doing so, we automatically could have like those different kind of processes. So since we are going beyond the Eichner, so we could have like the change in the transverse precision space all the time, and also we could have multiple gluon emission and absorption along the process. And since we're doing the calculation on the amplitude level, so all different kind of possible trajectories are taken into account automatically. So in this method, so what we started first in the beginning, so that's during my PhD, that look at the simple case where there's only one quark sector, but there's still like multiple modes in the momentum, color, and elastic space. So then the process we started that we start with a bare part state, and then when it enters the medium, it interacts with the background field from the medium, and through the interaction, it can take different momentum state and also a different color state. So this allows us to study scattering and also the broadening in both momentum space and position space. And then later on, we end in the next Fock sector, which is the QG Fock sector. So now the system, the quantum system of the jet is a superposition of quark state and quark gluon state. And the process, when we cannot consider that, so still we start with a bare quark. And when it enters the medium, it interacts with the background field. But also since now we have the qg component, it can emit and absorb gluon. So this process happens at the same time with the background field interaction. And so in the end, we have a linear combination of different quark state and also different quark gluon state. And then one can interpret the gluon radiation by summing over the probability of the quark gluon component.
I have a naive question. So I was thinking about the power accounting. Just something I don't understand. Each interaction of the background field presumably also come with a coupling.
Yes.
So does that also count, like when you're counting different orders? Like if,
okay. So for me, I'm doing non-perturbative calculation. So I do not do the power counting. Or in other sense, so I will give more details later. So I do truncation on the Fock space. So I have quark and quark gluon, but I don't have qjj. So that's my truncation. But within this Fock space, so all powers of interaction are included.
mm-hmm.
And I think maybe your question is more related to like what other people do perturbatively. Yes. So the Wilson line is that so you sum over all orders of this AU, but then when you think about the gluon emission, so there you count the power.
Okay.
So it's different.
Thank you.
Okay. And then, so now what we're currently doing is that we consider different scenario. So the thing that, so if you think about the quark jet that entering the medium, so this quark, it can be produced far before it enters the medium. So it will have some time.
So in your case, the interaction with the color field also happen after the emission.
Yeah, it happens.
So this
so it happens here. So together with the emission. In this case, so we let the initial state to be addressed quark. So there's already gluon component there.
Yeah.
And then after it enters the medium, so the gluon emission and the interaction with the background field happens at the same time because that's in the full Hamiltonian.
Okay.
Yes. So okay, maybe let me put it this way.
The state is different. What do you mean by dressed quark? I mean the state is.
Dressed quark is that so. Oh, okay. I will explain it. So here.
You can explain later. Maybe if you want. If you come back to this point, that's fine.
Okay. Yeah. I will come back to this. Yes. Here, just the physical picture. We're considering if the quark comes from far before it enters the medium, then it will have some time to develop some gluon cloud. So that's the dressed quark state. And then when this dressed quark state enters the medium, it is still like interaction with the medium as before. So there's also gluon emission absorption and also the medium interaction. And the nice thing about this picture is that when we know what the dressed quark state is, so when it interacts with the background field, it can have the center mass motion excitation. So meaning that its intrinsic structure remains the same, then this is just the elastic scattering. But it could also happen that the internal structure of the system change. So like it could have a different qj component compared to the initial dressed quark states. So those and also the pure quark gluon states can be interpreted as the gluon radiation because it's no longer the initial dressed quark state. I will explain it later how we describe the dressed quark state in our formalism. Okay. Yeah. So I will talk about the method, which is a lifelong Hamiltonian approach. And so in short, that's called TB of Q. And I will explain how we apply it to this problem and how we get the just state. So the method I'm using is the time-dependent basis lifelong quantization. So essential part of formalism is that it uses the lifelong dynamics. So when we do the quantization of the quantum field, we quantize the field on the equal lifelong time surface. So the lifelong time is defined as x plus equal to x0 plus x3. So if you are more familiar with the instant form, so where the time is instant and the field is quantized on the equal t surface, like t equal to 0 surface like this. So in comparison, the front form is that for the equal x plus surface, so it's like attached to the light cone. So this is now the, so x plus would be the lifelong time. And then what conjugate to x plus is now the p minus. So that is the lifelong Hamiltonian in this formalism. So a main advantage of the lifelong dynamics versus the instant time dynamics is that you have the maximal number of kinematical operators in the Lorentz operator generator groups. So there is now 7 kinematic operators. And so with the lifelong dynamics, so one do the with the lifelong dynamics, one can do canonical quantization of the quantum field and then get the Hamiltonian, which is now P minus the lifelong Hamiltonian. And for a time-dependent process, this obeys the time evolution equation. So this is a Schrödinger time-dependent Schrödinger equation on the lifelong. And then by solving this time evolution equation, one can know how the quantum state, this psi, evolve at different lifelong time point. And the way we do it is that we use a non-perturbative treatment. So if you're familiar with the time evolution equation, you know that the solution is past order integral in the time direction, so which is now the x plus. And so the perturbative way that you can expand this past order exponential in the powers with constant. But instead, what we are doing is that we do not expand this, but we treat it as a product of many small time steps. Okay? So such that from an initial state, like size, and one can apply the operation and each time step sequentially. And then, so in doing so, we contain like a different order of powers of information versus perturbative treatment. So that's the method. And then in the numerical calculation, we also choose a basis representation. So to put it simply, in that by choosing a set of basis states beta, one can write the state and anytime psi x plus and the coefficients times the basis state. So it's a linear combination of basis states. So, and with the choosing basis state, we have the Hamiltonian and the evolution operator, and also for given initial state, then one can get the evolved state by doing the numerical simulation. So that's this method. And then to this problem, which is the immediate quark evolution. So using a simpler version of this space-time is that we let the quark moving close to x plus direction. So the medium is along the x minus direction. So we treat the quark and the quantum state, and for them we use the MV model to discrete. So the medium serves as a background classical field. So we start with like from Hamiltonian. So in this sense, in this process, it comes from the Q+Lagrangian with an additional background. So here we distinguish this A mu, which is the gauge field, and this curly A mu in red, which is the classical field in the medium. And then by doing the Lorentz transformation, we get the Hamiltonian in the q+qg space, which contains 3 terms. So the kinetic energy term, and then there are 2 interaction terms as shown here. So in both quark to quark and qg to qg sector, there's an interaction of the Fock particle, so which has a quark and the quark gluon in the system, interacting with the medium background field, so shown with this vertical gluon line here. And then there are also the transition between the quark and the quark gluon sector. So those are the gluon emission absorption interaction. So that's the Hamiltonian. And so a little more information on the background field is that we use the MV field.
Can you go back to the table on this state?
Yes.
This is just a different Fock state, right?
Yes, just different Fock state, yes.
And you said something about the Hamiltonian. Is the Hamiltonian does not really matter. What's the state?
This is the Hamiltonian. Yes. Oh, okay. So this is the.
You're talking about measure elements of Hamiltonian between different states, but
yes.
Hamiltonian is just Hamiltonian.
Yes. So this is like a Hamiltonian matrix on a high level.
Okay.
Yes. So I will explain explicitly the basis I'm using. Yes. So with the basis states, like each Fock sector, each quark, so you contains multiple basis states. They have different momentum, different color. So they have different quantum state. And then of course the matrix element from different quark to quark would be different because it would have different kinetic energy. And then from quark to qg, so only the element that conserves the momentum could have non-zero contribution, the Hamiltonian. So this is just on the high level showing the Fock sector of quark and qg, but it does not mean that we only have one quark state or one qg state. And then a little bit more on the background field that we are using is that so we use the MV model field. So what it describes is that when the quark going through the medium or the background field and very high energy, it does not have time to see the dynamics within the field. But what the field looks like in the eye of the quark is a static color field. So this field can be think about if you think about the field from the heavy ion, you can think about the gluon that's generated from the color charge, which are the quark in different nuclei, and then those color charges, they are uncorrelated from each other, so they're independent. And in this model description, that the color charges are stochastic variables, so they follow this 2-point correlation relation, and its strength is characterized by this g² mu component. And this delta function, meaning at different position, they are uncorrelated. And then the field is solved from this reduced Yang-Mills equation, so which in the functional form is a 2-dimensional Poisson equation with a mg² acting as an infrared regulator. And what is often being used in this MV model is the so-called saturation scale. So it can be think about as the accumulation of the charge strength, which is g² mu, for the duration of the evolution time, which is the L eta. That is also the width of the background field. And then for the basis we are using that we choose the momentum states of the particle and the basis states. So for the quark, then the beta, so the basis states, so each basis states have a definite momentum of the particle. And then the state can be expanded in this basis space. So for the quark sector, and it's a different momentum states. And for the qg sector, now we have two particles. So the two particle basis states can be written as the product of the single particle state for quark and gluon. And then in specific for each basis state, it carries 5 quantum numbers. So kx, ky, and k plus are the 3 momentum. And then lambda is the elastic, and c is the color of the particle. And so in the longitudinal, for the longitudinal momentum, so we impose the periodical boundary condition and anti-periodical boundary condition on the x minus direction. And then correspondingly, the p plus is discretized. So when we describe the mode for the quark and the gluon, so their p plus takes discrete values. And then also in the transverse direction, we discretize the transverse coordinate space on the square lattice. And we also impose periodical boundary condition on the lattice. And then correspondingly, the conjugate space, which is the transverse momentum space, is also under a periodical transverse lattice. And then using this basis, so the total basis size for the q plus qg space is on the order of n perp to the fourth. So 2n perp is the number of sites in the transverse direction.
You don't count the longitudinal.
That's the k.
Oh, that's the k. Okay.
Yeah, that's the k. Yes.
Then the other one is n perp.
Yes. K and n. And then, so now we have the basis representation, so we can write out the Hamiltonian explicitly, and then also the evolution operator. So as I mentioned earlier, so the way we simulate the time evolution is that we write the evolution operator as a product of many time steps, and then at each time step, so the Hamiltonian contains all the 3 terms: the kinetic energy and the interaction with the background field, and also the gluon emission absorption term. And so numerically, what we do is that at each time step, so for the interaction with the background field, since the background field interaction is local in the transverse coordinate space, so we do that in the coordinate space. And then for the gluon emission absorption term, so we do that calculation in the momentum space, because this interaction preserves the total momentum, and then using like a method like a Runge-Kutta method, computational complexity is O(n), and for the Fourier transform is O(n) log n. So the total computational complexity of each time step is on the order of n log n. So that's for the time evolution. And then just to illustrate the method of how we do the time evolution on the high level is that we start with the initial state, and then we do one small step evolution. So that's the delta t, get to the next state. And then we do another time evolution, and till the end, we can get the final state. And then since we are doing this calculation on the amplitude level, so at each intermediate step, so the state contains the information of all the possible state in the phase space. And so for example, if we start with a single quark, then at the intermediate step is a superposition of all the possible state that is a linear linear combined into the state at that moment. Okay, so now I will talk about how we describe the Dresdel-Quark state. So for the Dresdel-Quark state, if you think in the Hamiltonian formalism, it's actually the QCD eigenstate in this Fock space. And the way to get the eigenstate is that we solve the eigenvalue equation. So here, for the Dresdel-Quark state, so this Hamiltonian is just the QCD part. So it does not contain the background field interaction, only the kinetic energy and the gluon emission absorption interaction. And then by doing diagonalization, we can get the eigenstate, which is the Dresdel-Quark state. And also here, so this is the time independent. You can think about it as the time independent Schrödinger equation. And so people usually define this HLC, which is this P minus times P plus minus P square. And then the corresponding eigenvalue would now be M square, which is the invariant mass instead. So the state you get is equivalent. So these two equations are equivalent. And the nice thing about the second form is that now the state itself you get is boost invariant automatically, in the sense that if you change, once you get to the Dresdel-Quark state, if you change its total central mass momentum, like P plus and P perp, its internal structure will remain the same. And then we also adopt the sector-dependent mass renormalization scheme to do the renormalization. So the procedure, put in simply, is that so for a given quark mass, so that's the physical quark mass. So for example, if you want to get the Dresdel quark wave function or charm quark, then you should put the charm quark mass here. And then
that's the current quark mass. MQ.
Yes, the physical quark mass. The whole system, the Dresdel quark.
Not the okay.
Not the bare. Yeah.
Not the quark. It's not the current mass. It's not.
Let me see. So it's the constant tube.
When you say physical mass, what do you mean? Physical mass, there could be many things. It means.
It's the mass of the Dresdel quark. So not the so a Dresdel quark could have the gluon cloud in it, right? And also quark component in it. What I mean is the mass of the whole system.
And then that could be different in the medium too, right? Is the Dresdel quark mass different in the medium with the background field?
With the background field. With the background field interaction does not depend on the quark mass.
It does not depend on quark, but it will influence. I'm asking whether it will influence your effective quark mass when you say Dresdel quark mass.
The short answer is yes. So more specifically that this is the physical quark mass, right? So what I mean is that the quark mass of the whole Dresdel quark state, and then inside the Dresdel quark state, so you have the quark sector and also the QG sector, right? And so for the quark sector, so this M capital Q, we call it the bare quark mass. So then this bare quark mass is mass renormalized by adding this mass counter term. So back to your question, so this quark mass in the quark sector, so that's what enters the Hamiltonian. So meaning that the kinetic energy of the kinetic energy term so depends on this bare quark mass. So in that sense, when the quark going through the medium, so having like different quark mass will make a difference. Does it make sense? So yes, so this mass counter term is determined by doing like through the diagonalization, we match the ground state eigenvalue with the physical quark mass. And so that's how we can determine the mass counterterm and obtain the wave function and the state of the dressed quark.
So in different Fock sector, you have different quark mass?
Yes, sorry, I missed that point. Yes. So in this sector dependence mass renormalization scheme is that so you do not renormalize the highest Fock sector. The argument is that the reason the bare mass get renormalized is because it gets fluctuation from the higher Fock sector. And here we have like q plus qg. So only the quark mass in the quark sector receives a counterterm, but not the qg sector. So now imagine if we, so in the next, if we add the qgg Fock sector, and then this quark in the qg sector will receive a different mass counterterm from the higher Fock sector. So
then the quark from the first Fock sector will receive a second contributor as well.
yeah, I think so. Yeah, so that's the sector dependent mass renormalization scheme. And then just to show an example is that, so this is what we obtained as the mass spectrum by diagonalizing the QCD Hamiltonian. So the vertical axis is the m squared. So I use tilde is, so I converted to the massless dimension. So I divided by the dp, which is the resolution in the transverse momentum space. And then, so we classify the spectrum into different groups shown as different columns here. So the leftmost column are the dressed states. So by saying dressed states, meaning those eigenstates, they have contributions from both the quark and the qg sector. And so in contrast, also all the remaining, the other states, they only have the qg component. So they are the pure qg states. So only these are the dressed states. And for those dressed states, so denoted as here. So you have both components, and here you only have the qg component. So the lowest state, also by doing the mass renormalization, so we match its eigenvalue equal to the physical quark mass. So the ground state is the on-shell dressed quark state. And all those excited dressed states, so they can be thought of as a dressed qg states. So in the sense that they have a large qg component and but a small quark component. So they are like a qg state that is dressed by a quark component. And then, so for all the other states, they are pure qg states, but they can be pure qg states for different reasons. So like here, so those qg states, they do not couple to quark because their helicity does not match. So if you think about the q to qj interaction, so not all the qg helicity configuration will couple to the single quark. And also their higher color excited qg space, because they do not have the same color quantum number with the quark, so they do not couple to the quark. And then there are also the group of states that their orbital angular excitation between the qj component, so in the relative momentum of the qj component. So that will forbid them to couple to the quark state.
What is the L delta? I mean, is the transverse momentum?
Yeah, I try not to go to that detail. Yes, so delta m is like the relative transverse momentum between the quark and the gluon. So L delta is like the orbital angular momentum number.
Also quantized according to.
Yeah, because we are on a discrete space.
I know.
Yeah.
But
yeah.
so this is the unit. I mean, what is the unit here? You don't have any unit here. It's 1, 2, 3, 4.
Yeah, it's a dimensionless. So you can think of it as the orbital angular momentum quantum number. So, but not exactly that. So like so 0 is like a S wave. So 1 you can think of as a P wave, and then D wave. But not exactly those harmonic oscillator because we are on a discrete basis. So something.
So anyway, this is a different transverse momentum. And what is the other side? What is
So those are the color states.
the
So
color? Okay.
yeah, so qg is a high.
It's a different color.
Yeah, different color. They do not couple to the quark. And then there are also the elastic. So
And the vertical is what? There's a mass.
yes, the invariant mass square.
Invariant
Mass
mass
square.
in which unit?
In the unit of the
mass?
it's a transverse momentum resolution. So we are on a discrete basis. So there's a unit of the transverse momentum that we can resolve. It's like a resolution of the transverse momentum.
Okay. Yeah.
Yes. So it's like this. So it's like this. So it's this dp. So for the transverse coordinate space, it's expand from negative L perp to L perp. So then in the momentum space, the unit of the transverse momentum is pi over L perp. So I use that to make it dimensionless. Yes. So that's the addressed part. And then with this spectrum, and also of course we also have the wave function for each of the states, and then we can this can help us further interpret the scattering of addressed part state. So if we start with the addressed part state, so this ground state here and the initial state, and after it interacts medium, it can have a transition to all the other different states. So if it remains as the initial state, so note here, this is the invariant mass square. So it could have different center mass momentum. So in that sense, if the state is still a ground state but have a different center mass momentum, then it's the elastic scattering. But if the state have a contribution of a transition to all the other states, then which means its internal structure changes, and we can think of that as an inelastic scattering and relate that to gluon emission. So that's the formalism, and the next I will talk about the results. So first I still start with the simplest case, which is single quark scattering, and then the quark plus qg, and then use them as a reference to think about what is the addressed quark scattering. So that's still the first work we did is consider just the single quark scattering, and here is just we verify the Eichner limit. So in the beginning, I talk about there's existing study on the Eichner limit where one can calculate the cross section analytically. And in our method, we can go beyond the Eichner limit. But this also means that we can do the Eichner calculation, and we should reproduce the Eichner results. And indeed, when you look at the total cross-section, elastic cross-section, and the different G square mu, different G square mu.
This is the cross-section scattering with the color field.
Yeah, the color field. Yes, yes. And G square mu characterizes the strength of the medium. So you can just think of from smaller G square to larger G square, the medium is getting stronger. So those colored markers are from our simulations, and then the curve is from the analytical calculation in the Eichner limit. So they agree in both the total and the elastic cross-section case. And then in the single quark scattering, we already observe interesting non-Eichner effects. So what we look at is to look at the transverse coordinate distribution of the quark over time. So from left to right, so the x plus is increasing. So you can think of from the initial state and then going to the final state. So the top panel is at p plus equal to infinity. So meaning that is in the Eichner limit. And then the lower panel has a finite p plus. So now the quark is moving at a slower pace in the p plus direction. And in the p plus equal to infinity, so that's in the Eichner case. So as expected, nothing should change in the upper distribution. So recall that what I explained about the Eichner limit is that when the speed of the quark is too high, it does not have time to change its transverse position. And so what this is, when this is reflected in the Hamiltonian, is that the kinetic energy term of the quark will vanish. So then the upper stays the same. And when we relax the Eichner approximation, so we have finite p plus, and now the Hamiltonian contains the kinetic energy term. And again, when we look at the upper distribution, it will change over time. So this is from the single event simulation. So there's some irregular pattern here when the diffusion happens. It's because at a different event, there's a randomness in the background field configuration. And when we average over 50 events, so those irregular pattern kind of smoothed out, and one can see a clear diffusion in the upper space. So that's the non-Eichner effect revealed in the single quark scattering. And then we do the quark evolution in the q plus qg space. So now it contains.
Can I go back?
Yes.
You said you have like solutions. This is the average over 50 events.
Yes, like this is a single event. So
This is just you do evolution according to your Hamiltonian.
yes.
And then when you say events, are you saying the different initial condition?
Oh no, same initial condition, but different event. What changes is the background field it change, and the different event, the configuration of the background field change, and that enters through the Hamiltonian.
They didn't say how do you change. So what is your background field? Event by event, you have different color configuration or yes, coordinate, correct?
Yes. Oh, okay.
You do monocolor sampling or?
Oh no, not.
So what is how your background field change from event to event?
Oh, sorry. My bad. Okay, I kind of little skipped through here. So in this MV model, so the color charges, so the field is solved from this color charge, and for each event, this color charge density, so which is a function under different x plus and x perp direction.
Yeah.
So that is different. So we sample it by treating it as a stochastic variable. So if you look at this correlation relation, so it's a 2-point correlation. So rho equal to g square mu, and then the delta function. The delta function meaning at different positions they're uncorrelated. But if you treat this, if you take the argument of these two rho and the same position, then you get the covariance of this rho square, which is g square mu square, and that is the Gaussian distribution. So this is the random variable that satisfies the Gaussian distribution at each point. So meaning that for so at each point, so the value of rho at each x plus and x perp point, it's a Gaussian variable that has its a covariance is g square mu square, and then but if you only sample it at one event, then it's random. And if you average rho square over enough a number of events like 50, the value is g square mu square.
So you're not doing monocolor simulation.
No.
You just solve your Hamiltonian evolution equation. But
yes.
In the Hamiltonian evolution equation, your source term is entered there as this.
Yes.
You're not doing sampling. I mean, so I still don't understand. What do you mean by event by event? But you are not doing sampling.
Okay. I'm doing sampling is that so in one event, meaning that I sample the field, and now the Hamiltonian is fully determined, right? And then I do the simulation. and then at a different event, I sample the charge differently because it's a random variable.
You still do monocolor sampling. I mean, that was saying.
Oh, okay.
How do you sample from event to event?
In that
Even
sense,
though
you
it's
can, but
random,
I don't.
You
Yeah, I
have
don't use.
so there is a random number in your.
Yes, the random number. Yes, the randomness is in the configuration of the field. And then, okay, and then we enter the qg component. So now we have now we can see both gluon emission absorption together with the medium. So this is just a gluon emission absorption in the vacuum. But I think I will skip this and just go to the inside of the medium. So what we see is that, so now the Hamiltonian contains both gluon emission and the interaction in the medium. So what happens is that when you look at the probability versus time, so we start with the initially it's a single quark state, so that with a definite p perp. So it's a single quark and a definite momentum state. So its probability will decrease over time, and then this dashed blue line is also the state in the quark sector, but it has a different quantum number compared to the initial quark state. So that will increase over time because the quark will interact with the background field and change momentum and color. And then what is the third line is the dotted line, which is the QG sector. So that probability will increase because over time, the quark will emit a gluon, so it will have a transition to the QG component. And so over time, what we see is that so the quark it change to different quark state, and also it will transit to the QG component. And so on the right panel is that we now change the background field to a stronger one, so characterized by a larger g-square mu value. And now the effect of the quark going to the different quark state that becomes more profound. So you have a larger, a more rapid increase on the dashed line. And then this initial quark will drop more quickly. And then when we look at the QG component, the probability, so in the end, it will increase more compared to the case where the background field is weaker.
This I assume this you integrate all momentum.
Yes, all momentum and the color. Yes.
And also the color.
Yes.
Some of the color, and then do you have to impose some kind of infrared cutoff for the group?
The infrared cutoff it comes automatically through
The lattice size or the steps?
The lattice size. So the lattice size, so we do have a zero momentum, but there's a resolution on the unit of the transverse momentum. And then in terms of the background field, the background field has a different infrared cutoff, so that's entered as the mg square when solving the two-dimensional portion.
So this will depend on your lattice size, like grid size, or?
Yes, because the lattice itself contains infrared and UV cutoff. Yes. And then, yeah, so this is showing the momentum distribution of the quark and the quark in the QG and the gluon in the QG. So on the left panel, so still from left to right is the time is increasing. And what happened to the quark is that through the interaction, it starts from the zero momentum state and then it broadens to different momentum state. And for the quark and the gluon in the QG sector, so initially they do not exist, and then later on they will appear. And just in comparison, so on the right panel, so what is different now is this P plus is a smaller P plus. So it's like the quark is moving much slower compared to the first one. And now we see there's this circular pattern in the QG sector for the quark and the gluon in the QG sector. This is because through the evolution, enter different run in the momentum space, so they have a different p-perp, so therefore they also have a different kinetic energy term. And so this kinetic energy term is like it gives the oscillation along the time direction. So that's why over the time evolution, one sees this oscillational pattern in the transverse dimension for the quark and the gluon. So that's for the single quark evolution. How much time do I have? Okay, trying to wrap up soon. Okay. And then some just some preliminary results on the dressed quark states. So if now we still look at the momentum distribution in the q plus qg state, but what different from previously is that so initially we do not start with a single quark, but we started with a dressed quark. And this dressed quark, so it has both quark and QG component. So what I plotted here is that, so the top panel is the quark in the quark sector. So you can see its norm here is 0.79. So only around 80% of the dressed quark has a quark component. And then this is the total momentum in the QG sector. So its norm is around 20%. So for dressed quark state, it starts with like 80% in the quark sector and 20% QG component. Of course, this is looking at the central mass momentum for the QG sector. So it's the same with the quark sector. But if we look at the individual momentum for the gluon and the quark in the QG sector, so you see this kind of combination of different momentum mode. So this state is obtained, but what I introduced earlier by diagonalizing the Hamiltonian. So that's the initial dressed quark state. And then over the time, over the evolution, and so the initial quark, then it quickly becomes a combination of different momentum modes. And in the end, it's like going into kind of like a thermalized state. So it's distributed in the full space. And also similarly, if we look at the total momentum of the QG sector, so the two-body component, it also goes through like a similar process. And then for the individual particle, the quark and the gluon, individual component in the two-body sector, so the initial state will also become will also transit to different momentum states through the interaction with the medium. It's here from this simulation result, we see that the transition, like from the distribution, is that the quark, it receives a stronger effect compared to the gluon case. So that still need to be understood. And then just in comparison, so if we go back to the single quark case on the same basis with the same basis parameters, and then we see the single quark, it will go through this momentum transfer to different momentum mode. And then still to compare, now we are in the same Q plus QG sector, but the initial state is a bare quark state, so not a dressed quark state. So for the quark sector, similarly, that we see, so the momentum becomes a different momentum distribution. And when we look at the distribution for the quark and the gluon in the QG sector, now we see a big difference is that if you look at so initially they do not exist. And when this quark and the gluon, they come to exist, they comes from the transition from the initial quark to the QG component through the quark to QG interaction that is in the QCD Hamiltonian. And this interaction is roughly proportional to the p perp square. So this is why that we see that the distribution that it is stronger at the large momentum point. So the color is denser in the corner. So that is become this quark and the gluon component that comes from the splitting from the initial quark. And so here we see the difference compared to the dressed quark case. And then now we have the dressed quark state, and we can rethink about the gluon emission in our formalism. Is that so previously when we think about gluon emission, so we sum over the probability of the qg component in the final state. But now since we have the eigenstates of the QCD Hamiltonian, which can be think of as like the coherent states. So you have a dressed quark and also the excited dressed states and also the pure QG states. So now we can think of the elastic scattering as only the center mass momentum change, and then all the other inelastic scattering and the gluon radiation. So now we have like two different ways to interpret the gluon radiation. So if we start with a single quark initial state, and so if we follow the first interpolation, so we calculate the probability of the QG component. So we see that as time increase, so this QG probability, it will increase. So here we only look at the very initial time of the evolution. So what we see is that when this G square mu may increase, so this probability actually it goes in the opposite way. So it decreases when the G square mu increase. This is because it's in a very early stage of the evolution. And so when you start with a single quark, it needs some time to develop the QG component. So now the background interaction, it kind of reduces the probability in the QG component. And when we look at this gluon emission in the second interpolation, so what we do is 1 minus the probability that it stays under dressed quark. So that's the elastic scattering part. So now this probability, the behavior is different. So we start with a single quark. So the 0, 1, so that line is in the vacuum. So its probability does not have sizable change in this quantity. And when the medium strength increases, when this G square mu increase, so this quantity, which is the gluon emission in the coherent state interpretation, it will increase initially, but later on it's kind of going through some non-trivial crossing between different G square mu, and then we still need to figure out the mechanisms. And now in comparison, for the dressed quark initial state, so different from previous slides where we start with the bare quark states. Now we start with a dry quark with a dressed quark state. So when we look at its QG component, so for the 0 curve, which is the red one, it will always stay the same because the dressed quark state is the eigenstate of the Hamiltonian and when of the QCD Hamiltonian, and when it's in the vacuum, it's always stays the same since it's the eigenstate. And when we put in the background field, so and the background field increase, so in overall this QG component increase, so meaning that the medium it promote the gluon emission of the dressed quark state. And in the second interpolation, I think this is the preferred interpolation for the dressed quark state. And when you start, because now we start with the dressed quark state, and over the evolution time, what is being non-dressed quark state can be think of as the gluon emission. So again, in the vacuum, it does not scatter because there are no background field. And when the G square mu, so when the background field increase, so this gluon emission rate is also promoted. That's the gluon emission. And then lastly, we look at the cross section. So I briefly mentioned earlier about the cross section on the bare quark. So now we have the dressed quark, so we can compare. But of course, the basis when look at is slightly different. It's because for a quark, when you think about the cross section on the background field, it's just this quark going to a different momentum and a color state. And now for the dressed quark state, when we think about its scattering, we need to compare with what happened when there's no scattering. So what happened when there's no background field? The dressed quark stays at the dressed quark. And then when there's the background field, so it can become the excited state. And then what we see is that if we calculate the cross section for the bare quark, which is the open circle, red circle here, and for the dressed quark, which is the open triangle here, that we do not see noticeable difference when we look at just the cross section. So that's the what we see here for the cross section. And then, so that's pretty much all. So to summarize, we developed a non-perturbative light from Hamiltonian formalism to study immediate jet, quark jet evolution from bare quark to dressed quark. So we investigate the evolution of the quark jet inside the SU3 called medium in the non-equinal regimes. And the main advantage is the method is that it has the accessibility to the evolved quantum state through the wave functions. And just some relevant is that, so tomorrow in the nuclear theory seminar, so Yang will talk about the application to the quantum simulation. It's because you can see we are using the Hamiltonian formalism to do the explicit evolution on the amplitude level. So that is naturally suitable to do it also on a quantum computer. So that's why I also make application to quantum simulation.
Okay.
So that's all. Thank you. There's a question.
Okay, Wenqing, please.
Okay, thank you for a very nice talk. I have probably like two very naive questions.
Yeah.
One is on the slide 35, I think.
Yes.
So I think during this slide, you mentioned that like the proportion of the bare quark and the dress quark is like 80% and 20%.
Yes.
I'm just wondering how do you determine this, like, this proportion, like why it's like 80-20%?
Okay, so that is solved automatically by diagonalizing the Hamiltonian. So if you recall, so earlier we are talking about, so this initial state is the dressed quark state. So that is the eigenstate of the QCD Hamiltonian. So meaning that when we diagonalize the Hamiltonian in the Q plus qg space, that containing all the quantum state like momentum and the color, then what we get is a linear combination. So I mean, for the eigenstate, it's a linear combination of different quark state and the qg states, and then I can calculate the probability of its quark component and the qg component, and that is the value we get.
Okay.
Explain.
Yeah, maybe like another like kind of another reason I'm asking this question is, then does this proportion depends on like, say, how long has this quark like, traveled before it interact with the color field?
Oh, so in reality it should, but in our formalism we are obtaining the dressed quark state by diagonalizing the Hamiltonian. So I think that is like the quark is traveling infinitely long. So then it becomes the eigenstate of the Hamiltonian.
I see.
Yes.
Okay, gotcha. And then like another very naive question on slide 29, I think.
Okay. 20. Yes.
Yes, yes. I'm just wondering, like, oh, why this like curve plateau like after a certain g squared mu? I would naively like just imagine it to just go up with the stronger and stronger
okay,
field.
okay, I see. Very nice question. So yeah, so like this total cross section, it's like its maximum is 2. It's because when you calculate, so if you think about the, so this is the cross section of a quark, then scattering of the background field. You can think about this is calculate the cross section of a particle through a external potential. So then the way the cross section is defined is that it sums over the final states of this transition amplitude square. So this transition amplitude square is that so you take the final state, project to the initial state, and subject to 1, which is the identity part. So the way that it maximizes is that your final state is just to have an opposite side to your initial state. So it's like you have 1 minus 1, you have 2. Do I explain? Maybe let me see. There's a more intuitive way to explain. Okay, so this is like a quark scattering of a classical background field. So we have like a finite range for the transverse lattice. So if you think about the scattering of a particle through a hard disk, so in quantum, the cross section, so the maximal cross section is that it's twice the area of that hard disk. It's because quantumly you have the contribution that goes from the refraction and the refraction. So one is the area of the disk, and then the other is also the area disk. So you have twice the areas of disk. So this is like why it is like 2 here. It's because when the g square mu is very large, it's like a scattering of a hard disk.
Okay.
And
It's essentially the unitarily limit.
Oh yes.
That in that case, it become a disk. The total cross section essentially become 2 times the elastic cross section. That's what you see.
Oh,
yes.
okay.
The total is about 2, elastic about 1 in that limit.
Yes. And in that, like the analogy, the analogous example I mentioned is like so elastic is half of it, and then the inelastic is the other half of it. So in the hard disk scattering, that's like so one part is the diffraction, and then the other part is the refraction. So that sums over as the 2.
Okay, gotcha. Thank you. And maybe just one quick follow-up question. So you did the calculation for quark. Can you also do the same thing for the gluon?
Yes, definitely. It's just I only write the code for the quark now. So so after I finish up what I feel like most interested, I will definitely go to the gluon jet and to see what happens.
I see. And you can also do like heavy quark, light quark. You can dial the quark mass, right?
Yes. That can be. Yes. Thank you.
Okay, gotcha. Thank you.
Thank you.
You have maybe a quick question. I hope it's a quick question. Earlier, there's a slide we were looking at the probability of having a quark versus a quark gluon component. As a function of
This one, okay.
I guess 2 questions. One, what does it mean to have a quark with a different quantum number?
Okay. So we start with the initial quark, then it has a 0 transverse momentum. Here's the up and the color 1. So the different quark meaning different compared to this initial state. Like it can have like for the states that has a different p-perf, or this interaction does not change the velocity, so it's always less up. But the color can change through interaction with background field.
Does that also mean? Okay. And then on the left plot, when I was thinking, again, this is completely out of my field, so it's a naive question. But if I look at this, it tells me that there's a very large probability of creating a quark gluon state relative, 40%. Right?
Yes, yes.
And then what that makes me think is if there's a 40% chance of creating a quark gluon state, there's also probably a relatively important quark blue component.
Mm-hmm.
Which makes me wonder if the Fock space is even close to sufficient to describe the physics, because if I have such a large probability of creating a gluon, there must be another large component, quark blue, and so is this really a good picture, or is it, what is, I guess, how much of the physics would change if you added the quark blue Fock space component? Because this tells me there's a large probability to make quark blue, so there must also be a relatively large probability to make quark blue, and then so on and so forth. Like the gluon keeps wanting to radiate. And I guess what I'm wanting to know is if there's a feeling of the sensitivity of the predictions to the truncation of the Fock space.
I think I agree with what you're saying. Yes, it suggests that the qgg, or even higher Fock sector, may be important. But here, I'm adding a qg because that's also a limitation, which is also the approximation of our approach, right? So we're doing non-perturbative, but we have our own approximation. So we start with this, and I think to really answer your question, how important is the next Fock sector, we need to actually do and the qgg Fock sector to see that. And then about this question, relevant but maybe seems a little bit far away, but still relevant, is that it's about this mass renormalization. I think so. So right now, of course, ending the qgg Fock sector is the next step. But for now, we only have q and qg. And to make things correct, or make things more close to the reality, is that through this renormalization, I think it could count the percentage of the qj component in the correct track. Because the way we do the marginalization is that we require the eigenvalue, which is the invariant mass square of the dressed Quark system, to be the same with the required physical Quark system. And so what is being dressed, or the fluctuation in the system between the q and the qj component, is taken into account through this mass coverage. So I think this, of course, this does not fully resolve the problem, but compared to the previous work that still have q and qj, but without doing this mass renormalization, in the result you're asking, we start with a single Quark term, and so this way things are more in the control when thinking about the Quark and qj components.
But I think the real interesting question is attempting to understand how much results would change if you were to, not just, within a given model, how predictive, but if you could have some attempt to, you add QGG and then 4 Gs and 5 Gs, if you had some ability to estimate the truncation error induced by the missing pieces of the Fock space.
Yes.
Which is obviously not easy, but.
Yeah, that's definitely my long-term plan. Yes.
Okay.
So after this QGG, yes.
Which will be exponentially hard.
Yeah, I can imagine.
So as I mentioned, that's why we call it the quantum simulation. So as I mentioned here, So the real computational expensive part is that this imperf to the force. It's imperf to the force because one particle you have imperf square, so two particles have imperf to the force. So when you have qgg, it will be imperf to the 6. So that's what will make it computational expensive. But that's definitely the direction that we should go.
Okay.
Okay, we should stop here, and then we can, we should stop online.